Okay, so let's continue our discussion on inner products. In this lecture, we are going to introduce the concept of an inner product space. And inner product space. So, in the previous lecture, we started with a vector space V. We started with a vector space V, and this vector space was to be considered over the real field or the complex field, right? Then we defined a certain scalar function on V, sort of like this, which sends every ordered pair of elements from V, say A, B, to scalar, some scalar, which obviously is in R or C. And this function was to be called a inner product, inner product of the elements, right? Now, there were certain properties of these inner products, if you remember. So property number one was that inner product of alpha plus beta with some gamma was same as alpha gamma plus beta gamma. Then we had the inner product of C alpha with beta is C times alpha beta. Then we had the inner product with inner product of alpha beta was given as beta alpha bar. And lastly, we had the inner product of alpha alpha is greater than 0 for all alpha not equal to 0. Using this inner product, we had defined what we call the norm of a vector, which was defined as the positive square root of this inner product of a vector with itself. So, inner product of a vector was defined as the, you can think of it as the square of the norm is defined like this, or typically we define by definition it to be the positive square root of the inner product of alpha with itself. And if you remember the resemblance each of these carries, so this sort of carries the concept of a dot product of two vectors. This carries the concept of length of a vector. Okay. So definition: a vector space V over F. F is clearly either real or complex. I won't be mentioning that every time. So vector space V over a real vector space or a complex vector space. So I'm just using the symbol F. The vector space V is said to be an inner product space, which we write as IPS, inner product space, if there exists a well-defined inner product on it. Okay. And we had several examples of inner products. Like if we had discussed this example. Like if you consider, let's say, if you consider Cn, then we had inner product on it as inner product of xy was written as summation xi yi bar I is equals to 1 to n, where x was given as the coordinate x1 till xn and y was given as the coordinate y1 till yn, right? This was a well-defined inner product. So typically Cn with respect to this inner product, which we also named as the standard inner product, forms an inner product space. This is a very typical example. Two most important classifications of inner product space, if I say, is that a finite dimensional real inner product space, a finite dimensional real inner product space is called an Euclidean space. The reason being, if you recall, if V is a vector space with say dimension n, and say V is a vector space over R, then recall V is naturally isomorphic to R, right? We know that Rn, the typical term of Euclidean space, is attached to this a topological space, or I should, yeah, you can think of it as a topological space as well, Rn, because You can think of it as any space. You can think of it as an algebraic space or a vector space or a inner product space. The typical word of Euclidean space, it basically refers to the fact that Euclidean geometry works on R. Works on R. Or in simple words, the what is the Euclidean geometry? Whatever the shapes you have studied in your preschool or high school, right? Circles, triangles, those sorts of geometrical concepts, the concepts of geometrical figures and the uh, algebras or the analysis or the geometrical aspects related to all those shapes, they get carried over to this space. On this space, those concepts of Euclidean geometry are satisfied. Right. Typically, Rn is called the Euclidean space, but since if you consider a finite dimensional real inner product space, so what are the aspects which you can relate to this? First of all, it's finite dimensional real vector space, which typically means that this happens that V is isomorphic to Rn. Moreover, uh, it's an inner product space, right? It's an inner product space, and since it's an inner product space, so the concepts of length of a vector, or the rather I should say just simply the concept of length, the concept of angles, these things are satisfied on V as they are satisfied on Rn. Since V is the inner product space, so these terms, they are valid on V in terms of the inner product, right? So that's why the Euclidean geometry isomorphically works on V as well, right? Because the concepts of lengths and angles they get carried over from Rn to V via this inner product, or they exist in V in terms of this inner product as they exist in Rn. Okay, so that's the trivial sense I was wanting to explain. And there is one more sort of an inner product space, which is a complex inner product space. A complex inner product space is called an unitary space. Is called an unitary space. Okay. Now, obviously, if you start with a inner product space, then you can naturally define a norm on it, right? It's because what I want to say is that if you start with the inner product space, then you can naturally define a norm on it, right? By definition. So if you have an inner product space, then this inner product space also has a norm defined on each of its vectors, right? Therefore, there must be certain properties related to these norms as well, which are quite derived from the properties on these inner this inner product, right? So let me just state it as a theorem. Theorem: if V is an inner product space, and then for all alpha beta in V, and what do you have? Say C in F. These are the conditions which should be satisfied. Number one, that the norm of C alpha is mod of C times norm of alpha. Number two, the norm of alpha is always greater than 0 for all alpha equals to 0. Number three, mod of alpha beta is less than equals to norm of alpha times norm of beta. Norm of beta. This inequality is very important, and it's called the Cauchy-Schwarz inequality. Cauchy-Schwarz inequality. And the fourth is, which is quite, you people have seen this previously in some cases or the other, which is the triangle inequality. The norm of x plus y is less than equals to norm of x plus norm of y. Okay, this is called the triangle inequality, right? Observe that if you talk about R, that is simply the real vector space, then this norm is if you just consider the standard inner product, if you just consider the standard inner product, then this norm, which would then be called as the standard norm, that's nothing but the modulus, right? That's nothing but the modulus. Okay, whatever, let's prove this out. Proof. Now see, 1 and 2 are quite obvious, right? 1 and 2 are from quite obvious from definition. You just apply the definition of a norm that it's the positive square root of inner product, and then you will eventually get it from the properties of inner product only. 3 needs quite a bit of attention. See, if alpha is 0, then there's nothing to prove, right? If alpha is 0, then it's obvious, right? So, what if alpha is not 0? Let alpha be not equal to 0. We consider a vector gamma, and we choose this vector as beta minus the inner product of beta alpha by the norm of alpha squared times alpha. Okay. Now, by definition, this gamma is not equal to 0, or it can also be equal to 0, whatever. But at least its norm, the square of its norm, it must be non-negative. Yeah, that's it, enough to say. But the norm of this is nothing but the inner product of beta minus the inner product of beta alpha by norm of alpha squared times alpha and with itself, right? So beta alpha upon norm of alpha squared times alpha. If we expand this out, you will find two terms will cancel each other, and the terms you will be left with are beta squared minus what will you should have here? Yeah, mod of norm of alpha beta squared, because you will get one term as inner product of beta alpha, one term as inner product of alpha beta. Then you can take the conjugate of the inner product of beta alpha to get inner product of alpha beta times inner product of alpha beta conjugate. Both of them will multiply together to give you mod of inner product of alpha beta whole squared, and beneath you have norm of alpha beta, norm of alpha squared, and this is greater than equal to 0. Then you can just solve this out, right? You can just solve it, right? Okay, you can just expand this out. That's a very easy, expansion. We're left with one more thing, right? Number 4. Number 4, observe that previously we had encountered the fact that norm of alpha beta square for any pair of vectors alpha beta, this is equals to norm of alpha squared plus 2 times the real part of the inner product of alpha beta plus norm of beta squared, right? This is something which we had done. But observe that the real part, I just write it down here. The real part of the inner product of alpha beta, this must be less than equal to the inner product of alpha beta, right? Because if you start with any complex number z, then the real part of z, this must be less than z, right? Less than equal to z. You can take the modulus. Sorry, you can take the modulus. Is the less than equal to real the modulus of the real part of z. Sorry, the modulus of z. The real part of inner product of alpha beta is less than equals to the modulus of inner product of alpha beta. Correct. Real part of z is less than equals to the modulus of z. That's quite trivial, because if z is equals to x plus iy, then its modulus is equals to x square plus y square, which is clearly greater than equal to x. Right. So if I apply this here, then what do I get? So this must be less than equals to norm of alpha square plus 2 times the modulus of inner product of alpha beta plus norm of beta squared. But then by Cauchy-Schwarz inequality, this is further less than equals to 2 times norm of alpha times norm of beta plus norm of beta squared. But then this is nothing but norm of alpha plus norm of beta whole squared. But just then taking the root on both sides, you get norm of alpha beta is less than equals to norm of alpha plus norm. Clear? Got it. This inner product has a very important conclusion, that it helps you estimate the distance between any two arbitrary points. How can we do this? Let me just explain this. Norm of x minus z, this can be written as norm of x minus y plus y minus z, and I am choosing this y in such a way that I know the distance between x and y and z. That's what I'm trying to do. That suppose you consider this space, but which is an inner product space, let's say. So it's a norm space as well. That is, it has a well-defined norm. Suppose this is the point X, this is the point Z, and this is the point Y. Suppose you know that you know the distance xy and you know the distance yz, then using the distance between x and y and z, you can define the distance between x and z, or at least estimate the distance between x and z. Because if you have written it like this, then this must be less than equals to norm of x minus y plus norm of y minus z, right? In some books, this is the definition used for triangle inequality. In some books, this is the definition used for triangle inequality. There is one more form of triangle inequality which is quite a bit reverse than what we just stated. Observe that if I start with any vector x, then I can write this as x minus y plus y. But then triangle inequality, I can write this as x minus y plus y. But then if I take y on the left hand side, I have inner product of x minus, norm of x minus norm of y is less than equals to norm of x minus y. Suppose this is statement number 1. On a similar basis, I can start with the vector y and I can write this as norm of y minus x plus x. But then I can write this as norm of y minus x plus norm of x. But then I can write this as norm of x minus y plus norm of x. And why can I do so? Because if I take minus 1 common from inside, it will come out as the modulus of minus 1, but that's exactly. But then I get norm of y minus norm of x is less than equals to norm of x minus y. Observe that statement 1 and statement 2, they give the fact that the modulus of norm of y minus norm of x, sorry, I should use the conventional order. Modulus of the norm of x minus norm of y, this is less than equals to norm of x minus y. This is often referred to as the reverse triangle inequality. Okay, this is one more. Now let us come to a very important case. The case is in this form. I guess you people should recall these from your +2 level vector analysis or vector the chapter on vectors. That is, suppose you consider the R2 plane, for example, you consider the R2 plane and you consider any two perpendicular points, perpendicular lines. Okay, suppose this is the line A, this is the vector B, and they are perpendicular to each other. Then what does A dot what is A dot B? So if you recall by formula, it's just modulus of A times modulus of B times cos of theta, where theta was the angle between them. But I said the theta of the angle between them is 90 degrees. So you have here, modulus of the vector A, modulus of the vector B times cos 90. We know cos 90 is 0, so it must be 0. Obviously, the same concept happens in R3 as well, that if you have two perpendicular vectors, then the dot product between them is always 0, right? Right. So since we have sort of generalized the concept of the dot product in terms of inner product, so we must define some sort of a perpendicularity, which in a more mathematical term we use the term orthogonality in case of inner product spaces. Okay, so because talking about arbitrary angles does not make sense when you talk about an abstract inner product space or an abstract vector space on which an inner product is defined. But orthogonality is something which you can talk at any case, right? Which you can talk in any case, and that will be more precise as we give the definition of an orthogonality of vectors. Definition: let alpha beta be in V. Then we say alpha is orthogonal to beta. Okay, beta. So V, where V is an inner product space. Then we say alpha is orthogonal to beta if and only if the inner product of alpha and beta is 0. Okay. We denote this as, the obvious symbol we would want to use is alpha is perpendicular to beta. But observe that If alpha beta is equals to 0, then beta alpha is also equals to 0, because if you have a complex number which is 0, then its conjugate is also 0, right? Observe, if alpha is perpendicular to beta, then beta is perpendicular to alpha as well, right? So therefore it suffices to say that alpha and beta are orthogonal. Okay, it doesn't require to say which is orthogonal to which, but it just suffices to say that alpha and beta are orthogonal. Okay, so we can obviously extend this concept of orthogonality to sets as well. For example, S contained in V is said to be orthogonal to some vector alpha in V if the inner product of, oh okay, yeah, I can define it in terms of inner product, right? That is, if alpha, inner product of alpha and S is 0 for all S in capital S. That is, alpha is orthogonal to every element of S, or every element of S and alpha are orthogonal to each other. In this case, we often use the notation alpha orthogonal to S. Further extend this concept, we can also say that S1 and S2 both in V are orthogonal if the inner product of small s1 small s2 is 0 for all small s1 from capital S1 and small s2 from capital S2. In this case, we use the notation S1 perpendicular to S2. Okay, clear? Later we will also see that starting with some vector, we can formulate a collection of vectors perpendicular to that precise vector, which we often call as the orthogonal complement. If I just give a hint to what I'm trying to say, is that if I start with some set S in V, then I can form a collection of vectors from V such that every such vector is orthogonal to S, and we denote that collection as this. So this is often called the orthogonal complement of S. We will precisely talk about this when we talk about the projection theorem on uh, on inner product spaces. Okay, clear? Okay, so we can also further extend this concept of orthogonality to something which we call orthonormality. Okay, so what is orthonormality? So a collection S in V, uh, which is orthogonal, which is an orthogonal set. Okay, what do I mean by an orthogonal set? That is, every distinct pair, of elements in S is orthogonal to each other, or is orthogonal. Okay, that is, for all S1 not equals to S2 in S, the inner product of S1 S2 is 0. Okay, if all pairs of distinct vectors in S are orthogonal. So we started with a collection S in V, which is an orthogonal set, is called an orthonormal set, if for all S in capital S its norm is 1. That is a collection of mutually orthogonal vectors such that the norm of each vector is 1 is what we call an orthonormal set. The immediate example which you can obviously relate is the standard basis vectors of Rn or Cn. Example, suppose we consider R3, then the standard basis vectors, we know that E1 is 1 0 0, E2 is 0, 1, 0, and E3 is 0, 0, 1. If you consider the standard inner product on R3, then what is the inner product of E1, E2? So it's summation over I is equals to 1 to 3, or let me just multiply them coordinate wise. So we will multiply the first coordinates correspondingly. So 1 multiplied to 0 plus 0 multiplied to 1 plus 0 multiplied to 0 is 0. Observe in a similar way, you can see that the inner product of E2 and E3 is also 0, and the inner product of E1 and E3 is also 0. Furthermore, observe if since we are talking about the standard inner product, we can also talk about the standard norm, which is the norm induced by the standard inner product. Norm induced by the standard inner product is basically the norm which is defined in terms of the inner product we are talking about. So the norm of E1 by definition, so it's, let's talk about square just. So square is summation over so we what do we do is we consider inner product of E1 with E1, right? So we have a component wise squaring and adding, right? So we have 1 times 1 plus 0 times 0 plus 0 times 0, which comes out to be just 1, but this implies norm of E1 is 1 because we talk about the positive square root. Similarly, you can also observe that the norm of E2 is 1, and that's same as norm of E3 as well. So observe that this collection E1, E2, E3, E1, E2, E3 forms an orthonormal set. In fact, an orthonormal basis as well, because after all, these elements form a basis of R3, right? Obviously, the same thing can be extended for any standard basis in terms of the standard inner product. The standard basis vectors of Fn, where F is again either the real field or the complex field, form an orthonormal set. In terms of standard inner product. Because if you consider any other inner product, they might not be orthogonal as well. Okay, let us talk about number 2. See, if you consider the line y is equals to s, okay, let me just write it like from a geometrical point of view. Okay, suppose you consider R2, and you consider the line y is equals to x and the line y is equals to minus x. Then observe that these are orthogonal to each other, right? So definitely their inner product should come out to be 0, right? But is it so? Let's check it out. So any coordinate on y equals to x is just the pair xy, and corresponding element in y equals to minus x should be in the form minus yx, right? Clear? Therefore, because x is minus y, right? I guess you can relate these. Yeah, the direction of the x coordinate changes. Yeah, we are doing it via origin, correct? Okay. Or let me not just talk about this. See, if I start with an element from this line, that says precisely xy, okay, it's correct. If I talk about an element in this line, then yeah, y is equals to minus x, right? So if I start with an element, minus y, then the y coordinate is x, correct? Yeah, okay, right? So what is the inner product? Xy dot yx. This is, so by the standard inner product, we're talking about the standard inner product. So it's x dot minus y plus y dot x, which is C. Right? Clear? Okay. Okay. See, what I'm exactly trying to do is that I just see this is y equals to x, right? And this is what I am trying to write this as x is equals to minus y. This is what I'm trying to say. So that's why we frame the x coordinate and y coordinate using these two relations in some sort. Okay, clear? Okay. So yeah, this is quite relevant, right? One more important example in terms of matrices is suppose V is equals to the collection of complex n cross n matrices, and we consider the matrix E of equals to PQ, which has only non-zero entry, which has its only non-zero entry in row P and column Q, and the non-zero entry is 1 and is 1. Okay, so for example, if I consider, say, suppose a 2 cross 2 matrix, suppose I consider, say, E2 1, and I consider this in C 2 cross 2, so I should have 1 in the second row and the first column. So I should have 1 here and all the other entries are 0. Okay. Then if you recall the way we define norm on matrices, so if I consider, if you recall the concept of inner product of matrices, if you recall, then EPQ, the inner product of EPQ and the inner product of say RS, this comes out to be the trace of their product, right? EPQ, ESR, yeah, product of SR, right? Am I doing it correct? I often forget these things. As far as I'm concerned, yeah. We had a B star, right? We have a B star. So if I consider a B star, yeah, correct. Okay, SR. Because there is no concept of a conjugate here, right? Because all we are talking about are real entries. The concept of conjugate is not there. Yeah, correct. Okay. But if you find the trace of this, then observe that it comes out to be delta QS times the trace of EPR, but then trace of EPR is delta PR, but then obviously observe that is indeed an orthonormal set, right? Yeah, okay, it's an orthonormal set, which implies that the collection of elements EPQ is orthonormal, right? I often fumble around because I do not have a well structured, you know, well structured plan to do these lectures. I just discuss the things which correspondingly come to my mind while speaking about these topics. Okay. Okay. Yeah, correct. Uh, okay. Now suppose I start with, yeah, okay. Suppose I start with a orthogonal set. What can I say about its linear dependence or independence? Okay. Observe that suppose um, say V1, V2 till Vn is an orthogonal set. Consider some non-trivial linear combination. Consider some non-trivial linear combination of these vectors. Okay. So I have some relation a1 b1 plus a2 b2 and so on and so forth till say a and bn. Okay, such that not all ai's are 0. Okay, some of them can be 0, but not all are 0. And what we try to actually do is that we write them sequentially. That is, if say a2 is 0, then a5 is 0, then a8 is 0, we take all the vectors which has coefficient 0 to the right hand side, and we sequentially write them as all the non-zero coefficients appear first, and then all the zero coefficients appear, and then we index these vectors accordingly. That is what I'm trying to say. That is, you know, suppose I have this of the form, say 1 times v1 plus 2 times v2 plus 0 times v3 plus 3 times v4. If we have of this sort, then we try to write this as 1 times v1 plus 2 times v2 plus 3 times v4 plus 0 times v3, and then we just write these indices so that they appear in sequential order. So it's 1 times v1 plus 2 times v2 plus 3 times v3 plus 0 times v4. Okay, because whatever indices are used in this set, it does not cause any problem to them being orthogonal or orthonormal, right? Okay. So what we can do is that we can say that j is the, say, j is the largest index. uh, j is from 1 to n, such that aj is not equal to 0. Okay, that is, every other coefficient after aj is 0. So it suffices to consider the non-trivial linear combination up till aj. Okay, therefore consider the non-trivial linear combination up till aj. So we have a1 v1 till aj vj equals to 0. But if I consider the inner product of this with respect to any arbitrary element vk, so I am a1 v1 till aj vj inner product with vk, right hand side should be 0 because inner product of 0 with vk must be 0, and this k is obviously less than equals to 0, greater than equals to 1. But if I distribute this up, observe that this comes out to be summation ai inner product of vi vk, right? I is equals to 1 to n. But this is an orthogonal set, therefore this must be 0 for all I not equal to k, and it's non-zero only for I equals to k. So this is nothing but ak inner product of vk with vk, okay, is equals to 0. Okay. Okay, consider this collection of vectors to be non-zero is an orthogonal. Suppose this is a non-zero orthogonal set, because if there exists some zero element, then there is nothing to talk about orthogonality with respect to that vector 0, because 0 precisely is the only vector which is orthogonal to any possible vector. So it just doesn't, it doesn't mean anything to talk about 0 being an orthogonal vector, right? It's a non-zero orthogonal set. But if it's a non-zero orthogonal set, then now from here we can observe that it's ak norm of vk squared is equals to 0, but this is always a positive element because none of these vectors vk's are 0. So this immediately means that ak must be 0. Right? So now since k was an arbitrary chosen index, therefore every coefficient a1 to aj must be 0, and which precisely means that every coefficient here is 0. But then that means, this means that the collection v1 till vk is linearly independent, which immediately gives us the theorem that any non-zero orthogonal set is linearly independent, right? Okay. Moreover, this has one more consequence, that is, if I consider a linearly independent sequence of non-zero vectors, sorry, if I consider a linearly independent sequence of orthogonal vectors, suppose alpha 1 till alpha m is a linearly independent sequence of orthogonal vectors, and say beta is a linear combination of these vectors, or we can think of beta to be in the span of these vectors. So beta is a linear combination of these vectors. Then beta is precisely of the form summation k equals to 1 to n, the inner product of beta with alpha k divided by norm of alpha k squared times alpha k. So this is the coefficient in each case. And this is very obvious to observe, as see beta is equals to of this form, right? So it's a1 v1 till a n vn. But then what is the inner product of beta with any ai? Sorry, any vi, right? So it's then precisely inner product of a1 v1 plus a2 v2 so on till a n vn till vi. But observe that this is nothing but ai norm of vi squared. This just comes from the steps of the previous theorem. But this means that ai is nothing but the inner product of beta with vi by the norm of vi squared. And now, so every ai is of this form. Therefore, beta, so a1 will be the inner product of beta with v1. Okay, we have chosen the vectors to be alpha 1, right? Yeah. So, okay. So this is alpha 1, this is alpha n, this is alpha I. Okay, correct. Yeah. So you have alpha here, you have alpha here. So beta, so this is just beta 1. So a1 is just beta 1, inner product of beta 1 alpha 1 upon norm of alpha 1 squared. Then a2 is beta 2 alpha, inner product of beta with alpha 2 upon norm of alpha 2 squared. So this beta is nothing but summation k equals to 1 to n. Each of these coefficients ai is of this form, right? So inner product of beta with alpha k upon norm of alpha k squared times alpha k. So you can consider this as a theorem as well. Okay. But observe our important corollary. We know that the maximal linearly independent set is just the basis of a vector space, if we talk about a finite dimensional vector space. Therefore, any collection of orthogonal vectors from a finite dimensional vector space can have at most dimension v number of elements, right? What I'm trying to say is you can frame this as a corollary that if the collection alpha 1 to alpha m is orthogonal in a finite dimensional inner product space V, then this element n, which precisely is the number of elements in this orthogonal set, this must be at most dimension V, because this collection is linearly independent, right? Observe one more thing, which will be conclusion of this lecture, that suppose I talk about R3. What are the maximum number of possible mutually perpendicular vectors or mutually orthogonal directions in R3? Observe that there are only three, precisely the ones parallel to x, the ones parallel to y, and the ones parallel to z. There are no more possibilities. So on in R2 as well. There are only two mutually orthogonal directions, ones parallel to x and ones parallel to y. So this gives us often a geometrical intuition that so often the collection of all these mutually orthogonal directions are called the geometrical dimension. This is called the geometric dimension. So geometric dimension is precisely the number of possible mutually orthogonal directions in an inner product space. And the dimension of V, the precise dimension of V in terms of its basis, is called the algebraic dimension. Now precisely what we have seen is here that the geometric dimension is always less than equals to its algebraic dimension. But can we say the reverse inequality? That is, the algebraic dimension must also be less than equal to geometric dimension. But furthermore, what I actually want to say is that is the geometric dimension must equal the algebraic dimension of an inner product space. Okay, and this is indeed true, and that's a conclusion which we can draw from what we call the Gram, what do we call it? The Gram-Schmidt, yeah, I guess this is the spelling, orthogonalization process, which says that, or which gives a constructive proof that if you start with any finite dimensional inner product space, then you can always construct an orthogonal basis to it. So if you construct an orthogonal basis to it, then it surely always has an orthogonal uh, basis, and hence that orthogonal basis will precisely give you the number of the maximum possible number of, or the total possible number of mutually orthogonal directions, and then that must be exactly equal to the algebraic dimension as well. Because observe in here that in R3 your algebraic basis is just 3, which is exactly equal to its geometrical dimension. Clear? So that this will be the topic with which we will start our next lecture. So meet you guys in the next lecture.